giving continuity to our roundtable. Let's call the next speaker, Mr. David Warheit. Professor David Warheit is graduated at Harvard, Michigan, has had a doctorate in physiology in Detroit, and was worked in the National Institute of Health, had some doctorate and postdoctorate titles, and also in the environmental and health science. He worked with pulmonary diseases, moved to the laboratory DuPont to develop his research in lung toxicology. He works with toxicological lung mechanisms and equivalating risks, fibers and nanomaterials. Dr. Warheit is co-author of more than 100 publications at International Life Science Institute, got the award of Kennedy Mordrage in '93 in Hanover, Germany, for contributions in toxicology by a young researcher, and Hub Awards in reference in toxicology in the year 2000. Dr. Warheit also came to the diplomatic status in the Academy in the American Chamber of Toxicology in '98. He's working in assessment committees of the National Institute of Health, of bioengineering and age, and worked in research about cancer IARC. Toxicology projects, participation at the International Life Science Institute, health and sciences of the environment, and several editorials in newspapers and journals. He is associated editor in inhalation toxicology and toxicological sciences. He works at Assay Talk about nanomaterials and health science as a counselor at the National Program of Toxicology Nano Working Group.
Thank you very much, Madam Chairman. Thank you, William, and the organizing committee for inviting me. It's a pleasure to be here. I'd like to talk about particle surfaces and tell you a few stories. First of all, I'm going to, because I'm a visual person, talk about lung structure. You may know where particles go, or may not know, when inhaled, where they go in the lung and how they're handled. And I'm going to talk about how that happens in the rat. And then I'm going to talk about what risk is and how essentially it's a component of essentially exposure and hazard, and how we spend a lot of time measuring hazard. And then I'm going to talk about 3 different studies that we use with nano TiO2 particles and nano quartz, in part to learn something about nanoparticles, and secondly to challenge the dogma that all nanoparticles are always more toxic than fine-sized particles. So just for definition, let's go with nano, less between, or ultrafine as being 1 to 100 nanometers. And I just want to also mention at the outset, even though I focus on incidental exposures, and that is we try and limit the exposures to nanoparticles or reduce them. But you should know that the other end of it, and we heard plenty of this yesterday, is intentional exposures. And that is in nanodiagnostics and nanomedicine, people intentionally put nanoparticles into the body to do various things. So although in both cases we have to know the biology, I think it's very interesting that in one case we're trying to limit or reduce exposure, and the other we actively put it into the body. So let's start with a picture of the lung for a few minutes, and this is a scanning electron micrograph of the left lung of a rat, and we can see here, down here would be the trachea moving distally out to the pleura, and these are the airways. And one thing that you can notice is that The main function of the lung, although we like to talk about effects of particles and things like that, is really exchange of oxygen and carbon dioxide. And you can see here that greater than 95% of the surface area of the lung is designed exactly for that. These are alveoli. It has great surface area. You may have heard astounding figures like tennis court surface area and things like that. And we can never forget that that's a major function of the lung. And with an apology to the airway biologists, I'm going to call the airways here just tubes to take air and particles down to my area of interest, which is the junction of the end of the airways, terminal bronchial and alveolar ducts, and that's where the action happens. So at a higher magnification, if we're looking in this area here, we see the end of the terminal bronchiole, which has a variety of cells, clara cells, mucus cells, ciliated cells, and the alveolar duct here. And I'm going to show you in a minute where inhaled particles deposit initially. And it's, you can see here in the rat, this is the first alveolar duct bifurcation. Second, third, they're about 3 to 5 till you reach the end of the pleura. In humans, it's 10 to 22, so it's a matter of scale. So after a 1 hour exposure to iron particles, we find that particles deposit at the, preferentially, at least initially before clearance. Here's the end of the terminal bronchiole, alveolar ducts here. These arrows point to individual iron particles. And one of the reasons I like using iron is because we can backscatter it in the scanning electron microscope. And you can see here the same image at a higher magnification. Here are individual particles which have deposited at these alveolar duct bifurcation sites. And for size reference, here are red blood cells. These are 5 to 7 microns in diameter. These fine particles are about 1 micron in diameter. And so this is not unique to inhaling particles because also inhaling asbestos deposits in these same regions. This is a micrograph that was taken from many years ago when I was at NIHS with Arnold Brody. These are serpentine chrysotile asbestos fibers depositing preferentially on these alveolar duct bifurcations. And then when we look 24 hours later to see how low toxicity particles are cleared out of the lung, this is a low magnification. This is the end of the terminal bronchiole here. So here's an alveolar duct here, another here. This is the first alveolar duct bifurcation. I'm going to show you in higher magnification and backscatter that 2 macrophages have come to phagocytize particles here and then other macrophages move onto what's called the mucociliary escalator, coming up to be either coughed out or swallowed. So when we go to backscatter, you can see here black splotches with the iron particles. And if we go higher magnification, you can see here 2 alveolar macrophages, with this one with 10 to 15 particles in it, this one with 15 to 20. Here are some free particles. And if it was interesting or important for us to count the particles, we could do that in the backscatter image. So after phagocytizing the particles, these macrophages move onto the mucociliary escalator, which is the airway, which is actually a passive process of ciliated cells and fluid flux moving up, essentially a carpet ride, to be coughed out or swallowed. And you'll see in a minute that these macrophages contain a lot of particles, but that some contain very few. And this is the same image in backscatter. You can see here this one has a number of particles that have been phagocytized. This one has only 1. Here are some free particles getting a ride. So that's how some of the clearance takes place, particularly of low toxicity particles. But with higher toxicity particulates, this is now asbestos again. Here are 2 macrophages sharing a chrysotile asbestos fiber with an epithelial cell on the alveolar duct bifurcation. And you can see here this is going to be a lot more problematic to clearing this out of the lung. And looking at transmission electron microscopy, here are 2 macrophages with TiO2 particles which have been overloaded, which are sitting there, essentially, which will hopefully move out of the lung unless they're overloaded. But so the macrophage clearance process can occur through the mucociliary escalator, but another process is also translocation of particles. This is a transmission electron micrograph to show how thin this barrier is, the alveolar epithelial barrier. And this is necessary to exchange the oxygen and carbon dioxide. You can see here these red cells are essentially getting rid of about risk as a product of hazard and exposure. I'm going to talk primarily about our hazard studies because we're developing new products and we also want to determine how hazardous products are. But keep in mind that when we make a determination, as I'm going to show you, on hazard, essentially that does not mean risk, and too often that is confused with risk, something that's viewed as high hazard. If there is virtually no exposure or low exposure, then it has low risk. So these are fundamentally interdependent components that formulate the risk analysis. And I'm going to talk now about our studies on pulmonary hazards. Essentially, we have developed what we call our Pulmonary Bioassay, where we take particulates, and you can do this by inhalation, but we're using intratracheal instillation. And after we instill the particles in the lungs of rats, we have two sets of groups. One where we dedicate rats for bronchoalveolar lavage and measure a number of endpoints, and I'll go into that in a minute. Whole other animals are used for lung tissue analysis, but not the same animals. And the key features of our pulmonary bioassay and our hazard studies, I'd say there are four. One is dose response, two is time course, three is to use, particularly in these installation studies, benchmark controls so you can interpret your results, and to use relevant doses. So I want to talk three stories now. First is with ultrafine TiO2 or nano TiO2 that we did a few years ago with my then postdoc Christy Sayes, who's now at Texas A&M. And the idea was that we were going to use very small nano TiO2 particles, very small, and compare them against pigment grade and see theoretically they should be much more toxic. So this is our typical bioassay experimental protocol that we instill at least 2 concentrations so that we have a dose response. And key is to use a time course protocol, because if you look at one just first time point, particularly after installation, you're going to find a high level of effects. But the key is it at 1 week and 1 month a sustained effect? Because we want to know really whether these particle types are behaving more like quartz, which is our positive control particle. This is our most popular positive control particle, which causes a sustained inflammatory response. And so we're comparing it against this benchmark control. Now, one of the really important issues, the fourth issue that I didn't mention before, is characterization of the particles. And this is something, particularly in nanotoxicology, that has become so important, because if I just tell you I'm using TiO2 or quartz, that doesn't mean anything. Number one, I don't know exactly what I used. And two, you couldn't repeat those studies because you wouldn't know exactly what I used. So it's important to characterize. In this case, we were looking at anatase TiO2 dots and rods that were made by Christy Sayes at Rice University with Vicki Colvin before she came to join us. And we were comparing them against pigment-grade TiO2. And here's one of our initial attempts at characterization. So we're looking at particle size here, at surface area, and later we became more sophisticated. So you can see here that what we're comparing is something that has almost 30 times greater surface area, and this has 4 times greater surface area. So the dogma would say that these are more toxic than the fine TiO2, and here's our positive control. So I'm just going to talk about a couple of the biomarkers or endpoints that we use. And one is inflammation. So after you instill particles, and I'm going to show you how to read these graphs because I'm going to show them the rest of the talk. On the y-axis here is the parameter we're looking at, which in this case is inflammation. On the x-axis is we're looking at 4 different time points of all these different materials. So we're looking at 24 hours, 1 week, 1 month, and 3 months. And it's very important to do these time course experiments. So naturally you can see even when we instill phosphate buffered saline, which is our vehicle control, that we're going to get a transient inflammatory response, and even greater with the rods. But the key time points really are 1 week and 1 month. So are we seeing anything that's sustained? And you can see here that after the initial bump of instilling this bolus, that essentially there's no difference even among the smaller nano dots and rods versus the base versus the PBS. And so we concluded here that the pigmentary and the nano TiO2 were not different. And here's what we see at 24 hours. You can see here when you do a cytocentrifuge preparation, you can see macrophages, but you also see inflammatory cells in the form of neutrophils here. But at 1 week, in essentially the same groupings of animals, all you see are macrophages. The black ones have TiO2 in them, but you don't see the inflammatory cells, and that's very important to show that it's transient and not a sustained effect. And so we didn't believe our studies, so we repeated them and found the same thing. This time we included the benchmark control quartz, which, as you can see here, in terms of inflammation, causes a sustained effect up to 3 months, and I'm going to show you the tissue response later on. But essentially, we repeated the same studies. We saw the bump at 24 hours, but nothing was happening afterwards, which indicated to us that these nano dots and rods were not different in toxicity from the fine-size particles. Secondly, we did another study on different forms of nano TiO2 as well, because we were developing a compound at DuPont, which we called UF1 and UF2, and we were comparing it to UF3, which is known as P25, which is 80% anatase, 20% rutile. And here was a more full characterization. We looked at the crystal structure, the median size, both in water and in phosphate buffered saline. You can see it agglomerated here, looking at the surface area. But one of the key features was something measuring called surface reactivity using the vitamin C yellowing assay. That is, the particles of the 80%, 20% anatase here had a much greater surface reactivity, a little bit greater surface area, but we're going to see here this made a big difference in its toxicity profile. So we did a similar experimental design using the UF1 and UF2, which were the developmental compounds, comparing it to the UF3. Our negative control was fine, big TiO2, which is about 380 nanometers, and our positive control is quartz. And here you can see the quartz, which produces a sustained inflammatory response. You can see here that here's our PBS, and we get our bump at 24 hours, but essentially nothing thereafter. In the fine quartz, fine TiO2, nothing happening. In the two developmental compounds of TiO2, nothing was happening after 24 hours. However, in the UF3, which is the P25, you can see there's an intermediate response. Even though this is called TiO2, it has a different crystal structure, has a different particle surface reactivity, and has a lot of different other aspects, even though they're all called TiO2. So this was intermediate between the other TiO2s and the quartz. And when we looked at other endpoints, such as cytotoxicity, which is another measure of injury, we see essentially a mirror response to what we saw with inflammation, with the UF3 being intermediate between all the other TiO2s and the quartz. And we look at a third parameter of injury called cell permeability, or protein in the alveolar lavage fluid, and we see essentially the same response, that this is very different from the other 3 TiO2s in the PBS control. And then we use something called BRU cell proliferation, which is a tissue injury response, which again we use as one of our endpoints. And it looked almost the same as our lavage endpoints of injury. That is, the UF3 was very different from the other TiO2s. When we looked at the lung histopathology, or essentially lung morphology, this is normal lung morphology at UF1 and UF2 in pigment grade. You can see the terminal bronchial, these well-expanded alveoli and alveolar ducts. But when we look at the UF3, which is the other kind of TiO2, we see, number one, macrophage accumulation of particles and beginning of tissue thickening, not nearly as bad as what we see with the quartz, which is alveoli filling up with lipid-filled macrophages, which cannot clear the particles out of the lung. And we begin to see the beginnings of tissue thickening leading to fibrosis. And I wanted to now tell you a third story with nanoscale quartz. The idea is quartz is our positive control. It produces these effects. So we hypothesize that a nano form of quartz would be even worse than our regular positive control quartz. So this was published a couple years ago as well. And we compared a variety of quartz samples, some synthetically made, and Minusil is mined quartz. It's our positive control. So you can see here that it has an average size about 500 nanometers, but Christie Say's made a nano quartz that was 12 nanometers which had a much greater surface area, 90.5 versus 5.1. The crystallinities were the same, and the amount of iron in them was essentially the same, or very small. And we did the same kinds of experiments, but to our surprise, here's our Minusil, which we would expect to be sustained. But our nanoquartz was about the same. It wasn't greater, even though these particle sizes are much smaller. And when we looked at cytotoxicity, it was about the same. We didn't see a measurable change in potency. It's still a quartz kind of effect. Same thing with MTP, which is our microprotein measure of alveolar capillary permeability. Not a big difference. And the same with lung cell proliferation. So even though this is much smaller, we didn't see a big difference in size. And so we wondered what is going on. When we look at, again, the lung tissue at 1 month, before 3 months, we begin to see the tissue thickening. This is our typical quartz response. And at 3 months, or at higher magnification, we see a finer development of tissue thickening leading to fibrosis. The other feature of our quartz animal model is, as I said before, foamy alveolar macrophage accumulation, which never clears out of the lung. So when we compared all of the different quartz samples, here's the control. This is what a normal lung looks like. This is the Minusil, which is alveolar accumulation of alveolar macrophages and tissue thickening. And when we looked at the nanoquartz, there might have been a slight increase in potency, but essentially the same response. We didn't see a significantly greater response in the nanoquartz compared to the quartz. So we wondered what might be the factor that's common between these, and we did something called hemolysis potential of alpha quartz, which is an erythrocyte hemolysis assay. It's been known for 40 years that if you take red blood cells and you incubate them with quartz, they can cause release or hemolysis of the red blood cells. And in this case, we took red blood cells from a donor that I know very well personally, myself, and we combined it with the quartz, and essentially you can see here the ones with the highest surface reactivity, the nanoquartz and the crystalline, were about the same and were actually the most potent in our assay. And so we think that you can take all of these factors, but that the surface reactivity, or in this case hemolytic content, was the most common theme between the Minusil and the nanoquartz, which maybe accounts for the toxicity, because we had a fine quartz which had a lower toxicity, which did not have the same hemolysis content. So the point is that there are a number of factors which cause toxicity, nanotoxicity, but it's not just particle size and surface area. In the last 5 minutes, I want to just throw in another completely different issue, and that is how do you develop a new product if you're, say, a company, or essentially how do you develop a risk management kind of approach, because there are so few data on toxicity. And in fact, I didn't get into this, but doing exposure data can be very problematic, in part because of dose metrics, that is which metric to use, that is gravimetric, particle number, or surface area. But at least you can do some preliminary hazard studies. And about 4 or 5 years ago, DuPont undertook this with an NGO in the US called Environmental Defense Fund. In 2005, and they produced a document called the Nano Risk Framework, which you can download if you use this, framework email address, nanoriskframework.com. And the idea was to try and reach agreement on collaborating to develop early development of new products that you can try and assure that has some safety. So basically, this is a 6-part program that involves describing the material and profiling the life cycle, which is very important in terms of the material, hazard, and exposure. Sometimes you can't always do the exposure. And then you evaluate the risks. And this is what it looks like from a diagrammatic point of view. And I'm going to focus just on this part right here, profiling the hazards throughout the life cycle. And this happened to be for a new ultrafine TiO2 that I was just describing. So we came up with something that we call, with environmental defense, a base set of toxicity tests, which could give you some very good preliminary information about both environmental and human health toxicity without essentially doing 2-year studies, which would invalidate, which would make difficult development of any product. So basically the base set is a fundamental risk assessment, as I said before, requires hazard and exposure. This is an evolving concept to characterize the inherent hazards of nanomaterials, both for mammals and for ecological environments. The information gained can provide a basis for making reasonable decisions, and it's based on potential routes of exposure. That is, you have to determine whether your new product is going to be inhaled, dermal exposure, oral, or ocular, or all of the above, screening for potential carcinogenic effects, and also our aquatic battery screening for materials to rainbow trout, daphnia, and algae. And all of these tests, except for the first one that I described, which was our pulmonary bioassay, are OECD-validated tests, at least for chemicals. It's now trying to be determined whether they're useful for nanomaterials. So we used a skin irritation test. We're trying to move to an alternative test not using animals. Skin sensitization, the local lymph node assay, acute oral toxicity in eye, the in vitro AIMS and chromosomal aberration tests, and the aquatic battery, which are all OECD-validated tests. And just to give you a very brief, these were the results of this new ultrafine TiO2 that we had low toxicity, low oral toxicity. It was not a skin irritant or sensitizer. It was negative in our genotoxicity tests. It had low hazard in rainbow trout, and with daphnia. It had medium concern in algae, and that we think is because it essentially obscured the light. We're not sure whether that was inherent or just that algae needs the light to grow, and it had reversible eye irritation effects. So just to summarize again, that was our study with the base set, and these are some of the important criteria for physicochemical characterization, because you must start out at least with a minimum assessment of what you're testing. Otherwise, it can't be repeated and you won't know what you're testing. And we think that particle surface reactivity plays an important role in addition to size and surface area. Thank you for your attention. Obrigado.